All right, guys, so we're going to talk about something called the unit circle. And the unit circle is called the unit circle because the radius of the unit circle is 1 unit. So unit circle, anytime you see unit circle, you want to think radius equals 1. And we are going to talk about, I explained this to my grade 11 class, but does anyone, people who had battering class year, unit circle, does this ring a bell? No? Okay. So the unit circle is circle with radius 1, and I'm going to explain to you why every point xy is actually a point cos theta, sine theta for any rotation of an angle. So let's discuss this. So here is my rotation. This is just going to be, this is an arbitrary rotation that has been chosen of theta, okay? Some rotation. And we know that we always create a right angled triangle with the closest horizontal, right, to figure out information about our theta and about our side ratios and all that good stuff. So I'm going to create a right angled triangle with the closest horizontal here. This point, any point, of course, on anywhere on a graph is a point xy. Agreed? Okay, so we learned that in grade 9, right? This must be an xy coordinate. So to travel over to that xy coordinate, I must have gone a distance of x units. Keaton?
This is ringing a bell now.
Okay, that's good. And then I must have gone up a distance of y units. Okay, I went over x and I went up y, a certain number. I don't know what the number is. It's just x and y, right, in order to get to the point xy here. The radius is this, right? It's the distance from the center to the outside of the circle. So this is going to be our radius. All right, so if I were to set up the trig ratios in terms of x, y, and r, we did this in grade 11 last year, I would use my theta as my reference, and this would be opposite, adjacent, and hypotenuse. Okay, so can somebody tell me what is sine of theta in terms of x, y, and r? Surwa?
Y over r.
Y over r. What about cos of theta? Keaton?
X over R.
Okay, and what about tan of theta? Tan theta? Y over x. Okay, so in this case, we also have to remember that on the unit circle, radius is equal to 1. So if I plugged in my radius equal to 1 here for the unit circle, I get y over 1, and that makes this simply equal to y. So y on the unit circle is equal to sine theta, which we have here in place of y. And similarly, x over r, if I'm in the unit circle, then I have x over 1, and x is then equal to cos theta. So we replaced the x coordinate with cos theta at that particular location. Okay, so this is sort of the explanation. So every point on a unit circle, x, y, for any rotation of theta should be equal to the cos of that theta and the sine of that theta as the x and y coordinate. Okay? So that's our explanation, and that brings us into the second part of this, which is this cool little unit circle that we have here. Okay? So let me just give you sort of an explanation of this. I'm going to use these values as samples for us. So, but we'll talk about these quickly first, because these are our 3 important angles, right? Pi over 6, pi over 4, and pi over 3. So where do these come from? Well, based on what we just discussed above, we figured out that an xy coordinate for any rotation should be equal to the cos at that location of the angle and the sine at that location of the angle. So if I were to use pi over 6 as a sample, the xy coordinate at pi over 6 should be equal to the cos of pi over 6 and the sine of pi over 6. And then if we just use our special triangles, we just fill in the exact values of those. Okay, and then similarly, at the pi over 4 location, the xy coordinate at this location, it's labeled as root 2 over 2, and then root 2 over 2. This should have been equal to the cos of pi over 4 at this location and the sine of pi over 4 at this location. So that's where these points are being generated from. Now, cos of pi over 4, we usually say cos of pi over 4 is equal to what? What would this be equal to from the special triangle? If we looked at our special triangle, here's our special triangle for pi over 4. Sam? So 1 over square root of 2, right? Because if this is adjacent and this is hypotenuse, this is 1 over root 2. So where does root 2 over 2 come from? How come that's being plugged in for cos of pi over 4? Clayton? Yeah, so it's a rationalized version of that. So this is actually equal to root 2 over 2. Okay, so that's why you're seeing that in the unit circle. It's just the rationalized version of that value. And then similarly, for all these other angles, we're kind of going around and we're seeing that each of these is equal to cos of the angle and sine of the angle at that particular location. So that's the idea, okay? You will also notice, I want you to take note that all values that have pi over 6s as their reference angles, let's look at all of these values. What do you notice about the x and y coordinates at each of these locations? Emma?
It's positive and negative.
It's all of the x's are root 3 over 2, either a positive or a negative. And all of the y's at this location are all halves and negative halves. Why are some of them negatives and some of them positives, given what we know about the x and y axis? All the x's here, all the y's here, all the x's here, all the y's here. What do we know about those coordinates? Clayton?
Well, you can use like the cast rule.
I can use the cast rule, but also, what do I know, like if the x coordinate of this is negative, what do I know about all the x's on this side of the axis, Clayton?
They're all negative.
Okay, so it should make sense that all the x's here in this quadrant are negative. What do we know about the y's in this quadrant? If I go up on the y-axis, they're positive. So look at all the y's in this coordinate, in this quadrant. They're all positive, right? And all the x's for the points in this quadrant are negative. That's where the cast rule actually comes from, right? It's because the x's and the y's are positive and negative in certain quadrants, and that makes sine, cos, and tan and their reciprocals positive and negative in certain quadrants, right? Okay, so I noticed that all the pi over 6's are all points that are root 3 over 2 and 1 over 2, except some are positive and some are negative based on what quadrant we're in. Now let's look at all the pi over 4's. What do you notice about all these points that have pi over 4's as their reference angle here? Zach? It's all root 2 over 2, comma, root 2 over 2, right? The x and y coordinates are root 2 over 2 and root 2 over 2, but positives and negatives of each one, right? And then same thing with the pi over 3's. You'll notice that all the pi over 3's have the same points, so similar x and y coordinates, but some are positives and some are negatives. So all the x's are halves, all the y's are root 3 over 2's, but some are positive and some are negative depending on which quadrant we're in. I know that all x and y coordinates will be negative in this quadrant because this is the negative x-axis and the negative y-axis. So I should know, if I knew actually these 3 points right here, I could fill in the whole unit circle based on just positives and negatives and which way I'm going on the axes, right? Okay, so let's talk about these then. It says use the unit circle to determine exact values of all trig ratios for 3 pi over 4. So of course we just practiced this in our second unit and we did that by using the special triangles, using the cast rule. So if I were to use the nice little unit circle here, here is our 3 pi over 4. Now, of course, I would need to be able to fill in all the angle measurements and stuff like that and all the points around the unit circle to use this. But I know that sine of 3 pi over 4 should be equal to the y-coordinate at that location. What is the y-coordinate at the 3 pi over 4 location? Root 2 over 2. That's the answer. And it takes care of cast rule for me as long as I have the correct positives and negatives on the points. So that's it. Sine y is equal to the sine of 3 pi over 4 at that location, and that's root 2 over 2. X, the x-coordinate, so remember we said every point xy is cos and sine. So the x-coordinate should be the cos at that location, right? So the cos at the 3 pi over 4 location will be equal to the x-coordinate at that location. So what's the x-coordinate at the 3 pi over 4 location? Nick? Negative root 2 over 2. Okay, tan is equal to y over x. So if I wanted to find the tan of 3 pi over 4, I will do the y at that location, which is root 2 over 2, over the x at that location, which is negative root 2 over 2. What's anything divided by itself? 1, but it's a positive and a negative version, so this would be negative 1, right? And then for the reciprocals, all I have to do is flip them, right? So cosecant is the reciprocal of sine. That will be 2 over root 2. Secant is the reciprocal of cosine. That will be the reciprocal of the x value at that location, negative root 2 over 2. And then cotangent, reciprocal of negative 1, is just negative 1. Okay? This is an alternate way that we can do what we just did at the end of, or not at the end, but that we just did for lesson 2. Okay? This is how we can, if I know this circle, I could literally calculate any question. I can just use this whole circle for any possible question that I could have. So yeah, Keaton?
Will we have this circle on the test?
You will need to know the circle if you want to use the circle.
Wow.
Yeah.
Hang on, let me take a mental photo.
So I've already showed you guys how to fill in all these values, right? All the radian values. You just do the counting. 1 pi over 6, 2 pi over 6, 3 pi. If you know these 3 points are repeated all the way around here, except with positives and negatives in the quadrants where x and y are positive and negative. That's all that it is. So, okay, let's do it for 7 pi over 6.
It's not as complex as
7 pi over 6, I'm still on the first page here, is right here. Y will be equal to the sine at that location. So the y-coordinate tells us the sine value of 7 pi over 6. So what is the y-coordinate at the 7 pi over 6 location? Negative 1 over 2. Done. X will tell us the cosine at that location. So what's the x-coordinate there? Negative root 3 over 2. Done. So it's actually a lot faster than placing the angle, doing the whole cast rule. We can just use it for all the different questions that we have. And then remember, tan is y over x. So if I want to find tan at that location, I will do y, which is negative 1 over 2, over x, which is negative root 3 over 2. Okay, flip and multiply, guys. So times negative 2 over root 3. So I'm just flipping this guy and multiplying. The 2's will cancel. Negative times negative is a positive, and I'm going to be left with positive 1 over root 3 for tan. Keaton?
Can you walk through that one more time?
So I'm just taking this guy, So you get the y over x part, right? So I'm taking that, I'm flipping it, and you can change to multiplication. That's just how we divide fractions, right? Okay, and then your reciprocals are, of course, the reciprocals of those things. So cosecant of 7 pi over 6 is the reciprocal of sine, negative 2 over 1. Secant would be the reciprocal of cos, negative root 3 over 2, or sorry, it becomes negative 2 over root 3. And then cotangent, reciprocal of tan at that location, is root 3 over 1, which is just root 3. Okay, so that's how we can use the unit circle. I'm going to do this one really quick. We have 3 minutes, so we can do it. The unit circle, to determine the values on the edges here. Emma, you packed up too fast there. You thought we were finished. All right, I'll stop. It's fine.